Okay, so this is our last theory lecture, last introduction, talking about the fundamental theory for dynamics in this class, and then we'll follow this up with a two sample problems of applying the results of this derivation that we're going to do here. Okay, and what we're going to achieve is the general description of motion for 3D bodies that are rigid. They're not deforming. That's the only other way to make this more complicated, is letting those bodies deform. So what we're going to do is their equations of motion, meaning where they're true dynamical relationships. We have the kinematics component with the acceleration. We have the kinetics, and we're looking at the forces involved, and we're relating the two. Okay, that's what I mean by equations of motion, relating the forces and the moments involved to the change in the motion. Okay, this is named after Euler, and I'm not exactly sure why, but that's why we just call them Euler's equation, because well, they're grand. Okay, so they're ugly. We can already see that just the description of angular momentum in 3 dimensions is tricky. So then we go and do something with that through a relationship with the forces. It gets extra tricky. Okay, so that's the goal here, is just derive it, and then we'll practice using it next time. And again, keep in mind, last time we talked about the geometrical properties of the products of inertia and the moment of inertia. What we're looking for is, the main goal there was, can we find a principal frame where we can throw out a bunch of those terms? And so we'll have a complicated expression here in general, where a simplified version of that is what we're always looking for. And sometimes you can't get to that simplified version, and then the problems are just lengthy and tedious. Okay. All right, so our general equations of motion are as follows, right? Our translation is a trivial extension of Newton's second law for particles, where all we have to do to account for a rigid body is to say, well, this is the acceleration of the center of mass. This alone is 3 equations, because we have 3-dimensional motion. There's a vector equation, and so it has 3 components. Okay? The other general description of motion is that the sum of the moments about some point O, and we derived this previously, and this is general for 3D motion. Okay, the sum of the moments, so this is sum of the forces, causes an acceleration of the center of mass, translationally. So this is translation, and what we have down here is going to be rotation. So the rotational equation of motion is that any moments on an object about some point O causes a change in the angular momentum of this about the center of mass. And then we have this relative movement term, right? So this is the position vector of g with O. So this is just going to be, well, O is usually our primary reference frame, so that would just be the position vector of g from the origin of the coordinate system there, crossed into its acceleration. Okay. And these are just general, right? In fact, this, should we just leave it here? Well, let's see what we've done in the past with this. So in the past, what we've done is we've taken this general relationship that works in 3D, and we've applied it in 2D planar motion. Okay. And what we found was, well, we had different versions depending on what we wanted, right? So for an arbitrary point, the sum of the moments about a point O, arbitrary point O, was the moment of inertia of this about the center of mass, right? Well, there's a discrepancy, right? So it's moments about the object, moment of inertia about the center of mass, and so since there is a relative motion between those two, we have this added term. Okay, so this is general for 2D planar motion at an arbitrary point, for an arbitrary analysis about point O. Okay. We then said, okay, well, what if it's not arbitrary? Let's fix that point and not let it move in the reference frame. Okay, and this is what we get, right? So this is our fixed point O version, right? And all we did here was apply the parallel axis theorem, and basically this term, this is Ig, and then this is that parallel axis term, the md squared term. Okay, and then the last version was, well, what if that arbitrary point O was our center of mass, well then this term drops out to 0, right? Because then it would be the position vector to G from G is nothing. You wouldn't have to move anywhere. So that last term cancels out. Okay, this is now where we've chosen the mass center, so G, the motion about G. Okay, and that doesn't necessarily need to be fixed. Okay, that was what we did in 2D. Now, if this is 3 equations, what we did before was you choose one of these to go with as your equation of motion, and it was the most convenient. Right? We just choose whatever was the most convenient based on the problem setup, and then do your analysis. Now, this was combined with 2 equations up here. Because we're in planar motion, one of these equations is just trivially 0. There's no acceleration out of that plane in the rotation direction, right? Rotation axis, you don't get any motion out of that in planar motion. Well, we are going to get motion in that third direction when we allow for, 3-dimensional motion of our rigid bodies, as we're doing in this, in this last section of the class here. Okay, so that was just a review of 2D planar motion. Now in 3D full motion here, we first of all are going to limit ourselves to either mass center, well, so either of these last 2 options. So either fixed point or mass center analysis. So either have arbitrary O, but make sure it's a fixed point, or have that point of analysis be the mass center. Okay, so in that case, right, we have the sum of the moments is just the rate of change of angular momentum, or the sum of the moments about the center of mass is the rate of change of the angular momentum about the time rate of change of the angular momentum about our center of mass. All right, those are the 2 versions that we'll consider. Okay. Now the next thing we need to do is be careful with our coordinate system that we do the analysis in, that we express everything in. What we're going to do is we're going to affix a coordinate system to the body so that our moment of inertia values remain constant, and we don't need to keep changing them as the body sweeps through space that would otherwise be in a different reference frame or coordinate system. Okay. So this is what we're referring to as our moments of inertia and our products of inertia are constant. So the general picture here is that there's going to be a primary reference frame that you think is a good choice, maybe, that intuition tells you, hey, this is a good choice for doing analysis in. And well, in the end it's not. And this is usually would be the ground, the earth, the laboratory, whatever we're in. Okay, and then we have our body out here moving in space, and so it could be rotating. Okay, so the center of mass, perhaps it has a translational velocity, and then it's rotating maybe about that point. That's our omega value of the body. Okay, well, so we got rotation, and that means that looks that way, so it's kind of rotating about that point that way. Right, whatever it is, I'm just trying to represent general motion. So what we'd like to do is then come here and say, well, wherever on the body we are, we want to affix our coordinate system here. Okay, so this is definitely the body. Okay, that is moving, and we want to affix the coordinate system to the body, so we have what we call a body fixed coordinate system, or a body fixed reference frame. Okay, so let's do it, and it doesn't need to be at the center of mass. A good choice is something with the axis of rotation, but that rotation might be complicated. So let's just put it generally somewhere else, where this is just meant to be like a reference frame that's kind of at the surface here. Let's put X, Y, and Z, something like that. And it's just because it's a good choice. And it's purposely not the same as the primary. So in doing this, we are setting these 2, body and the secondary, equal to one another. Okay? Now the book, I just want to mention this, the book keeps these two as separate. They say, like, hey, if you want to go through the whole analysis and keep this as a separate reference frame from the body, well, that's fine, but then we have to have special notation in our Euler equations, and I'm just avoiding that because we are never going to have a case like that, or it just makes life more complicated. Okay, or our analysis at least. Once we do this, right, then the sum of the moments about O, right, expressed in terms of x, y, and z, by the way, right, which is the secondary reference frame. That's what we're saying is here. Our reference frame of choice is the secondary one, equals the rate of change of the angular momentum about point O, written in terms of the primary reference frame, but we want to rewrite this in terms of the body. All right, so then, oh, not plus, but equals. All right, so now we go to that conversion from the primary to the body frame. D dt stays there, but now we want to write this in terms of the secondary reference frame, or the body. If we do that, we then need an extra term for that accounts for the rotation of the body itself. So we have the rotation, the angular velocity of the rotation crossed into the angular momentum. Okay, and so now everything should be in terms of that secondary or the body fixed reference frame. Okay, remember h naught, our angular momentum about point O, right, that's still sitting out here in space. Angular momentum about point O, remember, is just that inertia matrix times omega b. And that is the omega of the body, the rotation rate of the body, where we wrote this out last time, right? This is ixx, ixy negative, negative ixz, iyx, iyy, iyz, minus izx, minus izy, izz. Okay? And this then is omega x, omega y, omega z. It's just I can't have three components, right? Where the I hat, j hat, k hat components are there. Okay. So from all of this, okay, plug this into there, plug all of these into there. So what we're going to do is going to take this, plug it into here. We have a time derivative, right? Well, the moments of inertia aren't changing in time, right? Which is why we did the body fixed reference frame. So let's add this in here, right? All expressed using secondary. So that's x, y, and z. X, y, and z. Okay? So that's the coordinate system about which we're going to write this. Okay, so now I'm going to write out the actual Euler moment equations that we get from plugging this up into here and this up into there. We'll have a time derivative of our omegas from that term, and then we'll have a crossing of our omegas with omega itself, both h naught, right? So it'll be h naught crossed into a matrix, and then also multiplied by this omega b. Okay, doing all the math, you get what follows. Okay, so we did it, and I will not guarantee that there are no mistakes in here, but I've tried to be really careful with all these terms. I would definitely refer to the book's equations about this, but remember the notation is a little bit different, and I'll mention this here in a bit and how we have to change the book's notation to get what we got here. And all that is that they didn't assume that the secondary and the body they didn't assume a body fixed reference frame. They assumed there was a secondary reference frame that was rotating that wasn't necessarily attached to the body. But I've made that assumption from the get-go, right? And so you see here, right, back to where we got this from, we got a term that's like the time derivative of our angular momentum, where the angular momentum is the inertia matrix multiplied by omega. So that time derivative is any of those omega dots. Omega dots here, omega dots there, omega dots there. In fact, there's 3 of them in each of our components of this equation. This is a component, 3-component equation, right? It's a vector equation. So these are the 3 components written out in each row, and each one has a time derivative of each component multiplied by a certain moment of inertia or product of inertia. Then you have all of these cross terms. Those come, anything that doesn't have a time derivative in it is due to this term over here, right? Omega crossed into h naught. Well, that's an omega. There's going to be some moment or product of inertia and then another omega there, right? And so there's, you see omega, omega, and then some inertia, right? Omega, omega, and inertia. Omega, omega, inertia. This is omega squared and inertia, right? So just an idea where all these come from. Okay, so it's a doozy, right? And you could be like, how could we possibly work through this in an actual problem? And well, you easily could. Just know that this is, a lot of times it's just, hey, do you know what the omega vector is? Right? Can you express it? And then can you take the geometrical properties? And if you can do that, right, if it's a basic shape that you can just look up all of the inertia values, and maybe a lot of them turn out to be 0, right, then this isn't so cumbersome. You basically cancel out a bunch of things. This is just general, right? So let's just recall one thing. Omega is the angular velocity of the body, or our secondary reference frame, which we set to the body, with respect to primary. Okay, so what we mean, that is, this is actually omega of the body. And when we have omega dot and the different components of omega dot, right, so omega just means omega x, omega y, omega z are the components of that. Omega dot, those are the omega dot, right, that is our angular acceleration. And that is the angular acceleration of the body with respect to primary. That is we should be writing angular acceleration of the body, or we could be. We just choose to leave it off from now on, right? Because that's the only omega word. Well, it's assumed in these relationships. Okay, here's my note about the book. The book uses a capital omega, that's what that is, for secondary reference frame in the equations, but we assumed a body fixed coordinate system. So the coordinate system we use, that secondary reference frame, is affixed to the body. So we've already assumed that these two things are equal, and you would need to do that in order to use the book's equations. Okay, make sense? All right, so here's now the key. Here's a good way to simplify our problems greatly. Okay, if we choose or find in our problem setup, find in the geometry of the shapes involved in their motions, if we can find a principal frame, and it's easier than you think, right? We'll work through some problems. They're the obvious choices a lot of times. If we can do that for our analysis, then, right, remember all of this means that our products of inertia, xz, iyz, all of them are 0. And look, right? That means, like, look at how many are 0, right? Well, none of these first, but that's 0, that's 0, that's 0. That all goes away. Okay, and in fact, I don't even need to rewrite it. What this is just what I'll put it in pink, my pink color here, right? So if this is the case, then what we need to solve is just this. Euler's equations reduced to this. Okay, not too bad. Less bad, all right? Now we just have to calculate 3 moments of inertia. And a lot of times, some of these, if there's a rotational symmetry, 2 of these are equal to each other, and maybe another one is 0 or something, so we can cancel more things out. Another case, maybe the omegas don't have all of their components. Okay, we'll see this in our example problems. Okay, much better, let's say, right? But still a lot of work to do. Okay, so let's wrap up this video with just a summary of our procedure that's going to follow here. So this is our procedure for solving dynamics problems for rigid bodies in 3D motion. Okay, and I'll try to follow this procedure in the example problems to follow. Okay, first thing, or sometimes I write it as step 0, and again, it doesn't always need to be exactly in this order. Maybe you get to step 3 and you realize, oh, I forgot a geometrical property. Yeah, do it at that point, right? But maybe you want to go into it and you kind of know which geometry values you'll need. So what we mean is calculate the needed moments or products of inertia, and at this step, let's look for the principal frame where we don't need to calculate any of the products of inertia because they're just intrinsically 0 just because of the rotational symmetry of the shape. We then go to a free body diagram. We then might need to introduce some kinematics relationships. Oftentimes maybe you have to do this after you do the next step, right? Because you write out your equations of motion and then you realize, oh, you know what? I'm going to need kinematic relationships to do this work, right? And then inevitably we solve what could be a big system of equations. Okay, so this will be the procedure we'll do next time, and that next time will be the last video in this class. Okay.